Hi everyone, this is Building Bytes. These episodes are excerpts from the Building Knowledge Base, available at info.building.inc. In these monologues, I will read research articles and thought leadership that we've published. If you learn something new, please consider following and leaving a positive review. Enjoy! Core Concept 1. Foundations of Asset Legibility. Section 3. Trust is an engineering problem. In complex asset markets, trust is created through auditability, controls, and verification, not reputation or narrative. Overview. In complex asset markets, trust does not emerge from reputation alone. It is produced by systems that make behavior observable, outcomes verifiable, and rules enforceable. This distinction matters because real estate involves long-lived assets, infrequent transactions, and significant capital at stake. When parties transact once every few years or decades, there is insufficient opportunity to build trust through repeated interaction. When assets persist across multiple ownership cycles, trust must outlast the individuals who created the initial documentation. This is why trust in real estate is best understood as an engineering problem rather than a relational one. It must be designed into processes, embedded in systems, and maintained through governance, not assumed based on brand recognition or prior dealings. Why trust breaks down in real estate. Real estate transactions involve multiple actors, extended timelines, and profound information asymmetry. Developers, contractors, architects, lenders, property managers, brokers, appraisers, and regulators each operate with partial visibility into an asset's history, current condition, and future obligations. What one party knows may not be communicated to others. What was documented at one phase may not persist to the next. What exists in theory may differ from what exists in practice. Trust erodes when information is incomplete or inconsistent. When stakeholders cannot determine whether they are working from the same understanding of facts. It erodes when records cannot be independently verified. When claims must be taken on faith because evidence is unavailable or its reliability is uncertain. It erodes when assumptions must be inferred rather than confirmed, when gaps in documentation force parties to guess about conditions, compliance, or performance. It erodes when responsibility is unclear, when no one can definitively answer who approved a decision, executed a change, or certified a condition. When trust breaks down, friction rises. Due diligence timelines extend as parties attempt to reconstruct missing information or verify claims they cannot independently confirm. Risk premiums increase as lenders and investors apply larger buffers to compensate for uncertainty. Transactions become more conservative as parties demand additional protections, contingencies, or concessions to offset informational risk. The cost of broken trust is not always visible as a line item, but it is real, measured in time, capital efficiency, and opportunities foregone. Reputation does not scale. Historically, trust in real estate has been managed through relationships, known counterparties, repeat interactions, brand recognition. These mechanisms work when transactions occur within tight networks where participants have direct experience with one another or shared connections that provide informal accountability. This approach functions at small scale but fails as markets become global, institutional, and automated. A developer in one jurisdiction may be unknown to lenders in another. An asset manager overseeing properties across multiple countries cannot rely on personal relationships to verify compliance in each location. Algorithmic underwriting systems cannot interpret reputation. They require structured data that can be processed programmatically. Reputation is also fragile. It can be damaged by a single failure, yet takes years to rebuild. It is subjective. What one party considers trustworthy may differ from another's assessment based on different priorities or experiences. It does not transfer well across systems. A strong reputation in one market segment or geography may carry no weight elsewhere. As real estate increasingly operates as a global asset class, accessible through digital platforms and evaluated by distributed stakeholders, trust mechanisms that depend on personal knowledge become bottlenecks rather than enablers. Engineered trust has components. Engineering trust replaces personal judgment with structural assurance. Instead of asking, "Do I trust this party?" the question becomes, "Can I verify the claims being made?" Trustworthy systems share 5 characteristics that make them reliable regardless of who operates them. First, auditability. Actions and changes can be reviewed after the fact, creating accountability through transparency. When decisions are documented with sufficient detail to reconstruct the rationale behind them, errors can be identified and corrected, patterns can be analyzed, and responsibility can be assigned. Second, provenance. Data can be traced to its source, establishing a chain of custody that allows stakeholders to assess reliability. Knowing who created information, when it was created, and what process generated it provides the context needed to evaluate its credibility. Third, consistency. Processes behave predictably, producing similar outcomes under similar conditions. When the same inputs yield different results depending on timing, personnel, or circumstances, trust in the process deteriorates. Consistency allows stakeholders to develop confidence based on repeated observation. Fourth, controls. Permission and approvals are enforced programmatically, preventing unauthorized actions and ensuring that only qualified parties can execute critical operations. Controls reduce the risk of error or fraud by limiting what is possible within the system. Fifth, repeatability. Outcomes do not depend on specific individuals. When only one person knows how to execute a process or interpret a result, that person becomes a single point of failure. Repeatable systems distribute knowledge and capability, ensuring continuity when personnel change. These characteristics are not philosophical ideals. They are design choices, decisions about how systems are architected, what data is captured, how processes are documented, and where controls are placed. Verification beats interpretation. A core distinction in engineered trust is the shift from interpretation to verification. Interpretation requires expertise, time, and negotiation. An appraiser interprets market conditions, property characteristics, and comparable sales to estimate value. A due diligence team interprets documents, inspection reports, and representations to assess risk. These interpretive processes are valuable but expensive. They demand specialized knowledge, consume significant time, and often require back and forth negotiation when parties disagree about what evidence means. Verification requires structure, rules, and evidence. It asks, does this claim match this record? Does this condition meet this standard? Does this approval exist in the required form? These are binary questions that can be answered through reference to objective criteria. Systems designed for verification reduce ambiguity. Stakeholders do not need to believe claims. They can confirm them through independent examination of evidence that is structured to support confirmation. The shift from interpretation to verification does not eliminate the need for expertise. Someone must still define what constitutes adequate evidence or appropriate standards, but it does move that expertise upstream into system design rather than requiring it repeatedly at each transaction. Once verification criteria are established, many routine checks can be automated or performed by less specialized personnel, reducing cost and increasing speed while maintaining rigor. Why technology alone is insufficient. Tools often promise trust through automation or decentralization. Blockchain platforms claim to create trust through immutability. Smart contracts promise to eliminate intermediaries. Artificial intelligence is presented as capable of verifying claims without human intervention. These assertions are misleading. Technology enables trust but does not create it automatically. A blockchain that records false information creates an immutable record of falsehood, which may be worse than having no record at all. A smart contract that executes based on incorrect inputs produces predictable but wrong outcomes. An AI system trained on unreliable data will generate unreliable conclusions. Without governance defining what information should be recorded, controls ensuring that only valid data enters the system, and clear accountability when errors occur, technology merely moves uncertainty from one layer to another. Engineering trust requires intentional system design, decisions about architecture, data models, and process flows that anticipate failure modes and prevent them. It requires defined roles and responsibilities, clarity about who can do what, who must approve what, and who is accountable when something goes wrong. It requires clear constraints on use, boundaries that prevent the system from being used in ways it was not designed to support. Trust is a property of the system as a whole, not a feature that can be toggled on. It emerges from the interaction of design, governance, controls, and culture. Technology is an essential component, but insufficient by itself. Financial implications of engineered trust. Markets price uncertainty. When an asset's condition, performance, or compliance status is unclear, buyers and lenders apply discounts or demand premiums to compensate for risks they cannot fully assess. Assets supported by engineered trust move through diligence faster because verification replaces investigation. They carry lower perceived risk because stakeholders can confirm claims rather than relying on representations. They support more confident underwriting because assumptions can be replaced with verified data. They attract broader participation because institutional investors with standardized requirements can evaluate them efficiently. This does not eliminate risk. Real estate assets face market risk, operational risk, regulatory risk, and numerous other sources of uncertainty that cannot be engineered away. What engineered trust accomplishes is making risk visible and measurable. When information about an asset's condition and performance is reliable, risk can be quantified, priced accurately, and allocated to parties best positioned to manage it. Opaque risk that cannot be measured because information is unavailable or unreliable, is far more expensive because it must be managed through blanket conservatism. Trust as infrastructure. When trust is engineered into systems, its nature changes. Compliance becomes continuous rather than episodic. Instead of proving compliance at specific milestones through intensive audits, assets continuously demonstrate compliance through ongoing documentation and automated checks. Audits become confirmation exercises, verifying that systems are operating as designed rather than investigating whether requirements have been met. Transactions become procedural rather than investigative. following defined processes to verify conditions rather than conducting open-ended inquiries to discover them. Trust becomes infrastructure, quiet, dependable, and largely invisible until it fails. Well-engineered infrastructure does not call attention to itself. Electricity is reliable. We notice only when the power goes out. The internet functions. We notice only when connectivity drops. Engineered trust operates the same way. When it works, transactions proceed smoothly. Diligence is efficient, and stakeholders have confidence. When it fails, when controls are missing, provenance is unclear, or controls prove inadequate, the cost becomes immediately apparent. Why this concept matters. This concept explains why many innovations fail to gain institutional adoption despite technical sophistication. New platforms, protocols, and processes are regularly introduced into real estate markets, often with significant venture capital backing and ambitious claims about transformation. Yet, adoption remains limited, concentrated in niche applications or pilot projects, rather than achieving broad market penetration. The constraint is not technology, but trust. Institutional investors, lenders, and other capital providers operate under fiduciary obligations and regulatory requirements that demand high levels of confidence in asset information. They cannot adopt systems that introduce new forms of uncertainty, even if those systems promise other benefits. They require evidence that claims can be verified, that processes are controlled, and that accountability is clear. In real estate, where assets are long-lived and capital commitments extend across years or decades, trust must outlast individuals, ownership changes, and technology cycles. It must be durable enough to survive disruptions while remaining flexible enough to accommodate evolution. Engineering trust is not about removing judgment. Judgment remains essential, determining what standards apply, what evidence is sufficient, what risks are acceptable. But engineering trust ensures that judgment is informed by reliable data, bounded by clear rules, and subject to accountability when it proves faulty.